Hello everyone, thanks for joining my talk, Bayesian Methods in Machine Learning. My name is Quan, I'm a PhD student in computer science at Washington University in St. Louis. My research actually focuses on the topics discussed in this video, so I'm very excited to go through it with you. Overall, I'll be talking about ideas and techniques used in machine learning that are based on Bayes' theorem or Bayesian statistics. The goal that I have in mind is to cover quite a number of topics at a relatively superficial level, and the materials covered might not be as detailed as some of you have hoped. This is so that we can maximize the likelihood that a person finds this video interesting. That said, I'll be also including references to more in-depth readings throughout, so you can find materials available online on what you're interested in. If you want the code used to generate the plots in this talk, you can also check out its GitHub repo. And with that out of the way, let's get started. We'll be specifically focusing on two main topics, Bayesian modeling and Bayesian decision making. Both are essential to Bayesian machine learning as well as any Bayes-centric decision making system. The first topic goes through some of the most common choices in terms of modeling a latent variable, including making inferences. If you are new to Bayesian statistics and inference, this discussion will help you get up to speed with the main ideas in this field. Otherwise, you are already familiar with the topic. The first part of this video can still give you a quick refresher, or you can skip to the second part about decision making. And with that, let's move on to our first topic, Bayesian modeling. We'll start with the canonical problem in Bayesian inference, estimating the success rate of a binary event. This event can be the phase of a flip coin, whether or not a new drug will have a positive effect on a specific patient, or whatever. We'll call this rate, which is a real number between 1 and 0, theta. To know the exact value of theta, we'll need to perform a survey on all possible instances of the problem, which is always impossible, but we can collect information in question on a sample of a population. We denote our data as D, which is simply a collection of zeros and ones. A 0 indicates failure, while a 1 indicates a success in whatever definition or question is regarding. And here is the size of our sample. With the data from this sample, we'd like to say something about the true success rate theta, maybe what value it most likely takes, or between what range it's most likely in. In other words, we'd like to perform inference on this random variable. The first component in our Bayesian framework that we need is our prior belief about theta, which is expressed as a probability distribution defined across its possible values. So in our specific case, it's a distribution with support between 0 and 1. Now the prior distribution or the prior belief varies from person to person. If you have some reason to believe that the success rate is fairly high, then your prior distribution will look something like this. Here, your prior distribution will have a lot more mass on the right-hand side, indicating that theta should be large. If you, on the other hand, don't have any idea about what value theta should take, you will want to express that using a uniform distribution between 0 and 1, which simply says that to you, all values are equally likely. Again, I want to emphasize the point that your choice of priors is unique to you and depends on your personal belief about the latent variable. How to choose an appropriate prior is a deep problem in and of itself, and I believe there's a talk at this PyMC on this specific topic. For now, we'll move on with our current problem of inferring theta. In addition to the prior, we'll also need the likelihood function to define the probability of the observed data given a specific hypothesis or a specific value of theta. Here we need a function computing the probability of D given a specific value of theta. We assume first there are k successes and n minus k failures in our sample data. This we can calculate fairly easily. If the true success rate is some theta, then each test in our sample has theta probability of being a success. Also, the tests don't affect one another, so each of the numbers in D is independent. So using the product rule, we can compute the probability of entire D as the product of the individual probabilities like so. If we treat the outcome of each test as a binary variable, we say that the variable follows a Bernoulli distribution with parameter theta. We usually call this the predictive distribution, as it is the belief about the outcome that we like to model. Okay, so we have the prior distribution and a likelihood function. Now we can apply Bayes' theorem to compute the probability of theta being of specific value, given our observed data as denoted here. We can compute this numerical numerator easily, as we already have access to both the prior and the likelihood. The question about how to compute the denominator in this question remains. First, we see that using the sum rule, you can rewrite the denominator as the sum of the numerator for all values of theta. But computing this integral is often intractable except for very specific cases. This is where we turn to sampling techniques to approximate the quantity. For example, say we draw samples from the prior distribution, then we approximate the integral as the sum of the corresponding terms of these samples. The idea is that if we can draw the samples in a way that the aggregate shape roughly resembles the shape of the whole distribution, then our approximation will roughly be equal to the true integral. Numerous sampling techniques have been developed, and MCMC is one of the most commonly used, hence the name of the tool that we're all using, PyMC. So either using samples as an approximation or actually computing the integral, we can actually obtain the posterior distribution. This value indicates the probability of theta being a specific number, having observed the data, computed as the product between the prior and the likelihood. A natural interpretation here is that the posterior is influenced by both the prior and the likelihood function, which makes sense because a posterior belief is a quantity driven by both a prior belief and the data that we observed. This calculated posterior probability defines the posterior distribution for theta. This is a function with the domain between 0 and 1 denoting a posterior belief about the possible values of theta. So that is the complete Bayesian inference procedure for this specific example. Let's now look at some visualizations. Let's say the true unknown value of theta is 0.3, so 30% of the time the event we're considering will result in a success. Say a prior belief about theta is encoded by this blue line, so before seeing any data, we believe that theta is around 0.8. Our sample data is the collection of 100 values, which I generated randomly using NumPy. It's visualized by these two bar plots. Each of the 100 values again had a 0.3 probability of being 1. Now after performing this Bayesian inference, a posterior distribution will become this green line. You see that the posterior now gives more mass to values around 0.4 and less mass to values far from it. This is exactly what we want because our posterior belief is pointing us to the right direction of the true theta. Now to estimate theta, we can use a central tendency statistic such as the mean or the mode of the posterior distribution. But more importantly, this posterior distribution allows us to actually quantify our uncertainty about theta. For example, if the posterior is highly concentrated around some number, then we are more certain about our belief. If the posterior is more widespread, then we are more uncertain about theta. Instead of the mean or the mode, sometimes we like to quantify the uncertainty of a variable by reporting, say, the 95% credible interval, which you can easily compute from the posterior distribution. Constructing this to the 95% confidence interval from the frequentist perspective, which in itself is a far more confusing idea, we can see that the Bayesian framework allows us to naturally quantify a belief about an unknown value. Overall, while this example is fairly simple, it demonstrates the power of Bayesian statistics in allowing the statistician to incorporate a prior belief in the form of the prior distribution and combining it with the observed data to finally get out a posterior distribution, which offers a natural way to quantify uncertainty as well. Moreover, even in more complicated applications, the Bayesian framework remains the same. So we first choose our prior and work out our likelihood function, and then we apply Bayes' theorem to obtain a posterior distribution. and we can finally manipulate this posterior distribution to extract out insights. Throughout this example, we work with one single latent variable theta, but the application of modeling a single variable can be very limited. What if we instead want to model a function, which in a sense is a collection of infinite variables, each defined on a point? Here we can turn to Gaussian processes, which are a natural and convenient mathematical object that allows us to use Bayesian inference to model a function. Okay, so Gaussian processes, or GPs, have a special place in Bayesian machine learning because they offer so much flexibility in modeling functions of various shapes and smoothness. In the simplest sense, having a GP prior on a latent function first means that we place a normal distribution prior on every point inside the domain of the latent function. A GP consists of a mean function, which specifies the central tendency of the latent function, and a covariance matrix, which defines the covariance of any pair of points within the domain. This covariance matrix, or the covariance function, in effect controls how smooth we like to model our latent function as. By using this normal distribution prior on the function, we can also derive the analytical expression of the posterior GP, conditioned on a set of observations as shown here. This math actually involves some matrix algebra and more complicated math. Luckily for us, most Bayesian software, including PyMC, actually takes care of this computation. Overall, all we need to know is that after this conditioning, the posterior GP gives us access to the posterior distribution of any point given any point inside the domain of the function. Let's now look at some examples so that we can have a visual understanding of what a GP can help us do. Say we have an arbitrary function defined on 0 and 1. We like to model it using a GP, which I'm showing the PyMC3 code here. A constant or even a mean zero function is typically used where there are many other choices to be made regarding the covariance function, with the matern 5-2 being one of the most commonly used. So those are our choices for this example as well. Now notice the covariance function has actually its own parameters, eta and L, which respectively scale the input and output of the function, thus controlling how the smoothness of the function should be. For now, we'll set eta to be 3 and L to be 1. Before observing any data though, our belief about the function entirely depends on the GP prior we place on it, which is shown here. The bold line is the mean function plotted across the domain, while the shaded region is actually the 95% credible interval of each of the point in the domain. This means that if you consider any point x inside the domain, its prior mean is 0 and its credible interval is between these two shaded regions. For now, there's nothing interesting going on as we haven't observed any data yet. Say we observe the value of the function at these specific points as shown here. After conditioning on these observations, we visualize the posterior belief again using the posterior mean and CI. We see that the posterior mean nicely goes through the observation and the CI is squeezed in the regions surrounding those observations. This is because within a smooth function, values in a small region are relatively similar, so after observing the value of a point, the uncertainty about the value surrounding that point decreases. The further we move away from the observation though, the larger the CI gets, and if we are far away enough, the posterior pretty much reverts back to the prior. If we take a vertical slice of this plot at any unobserved point x, we obtain our posterior belief about x. And that is the general procedure of using a GP to model a function, or in other words, doing regression. One note that I brushed over earlier is the choice of the covariance function parameters, which can be viewed as the hyperparameters of a GP model. Again, these hyperparameters specify the smoothness of the GP and therefore hugely influence the behavior of the posterior as well. For example, here are the posterior GPs when these hyperparameters have different values as shown here. Now, within a specific context, a user or a scientist can use her domain knowledge to find the best values for these parameters, but most of the time this choice can be arbitrary or inaccurate. A better, more Bayesian strategy is to go hierarchical and place a prior on each of these hyperparameters and perform Bayesian inference on them as well. After conditioning on these observations, some point estimate technique can help us set these hyperparameters. It is at this point that PyMC sets itself apart from other Bayesian modeling tools. For example, if you were to use scikit-learn's otherwise excellent GP implementation, you would either need to set the hyperparameters beforehand or use an optimizer to find their values, which doesn't allow you to incorporate your preference or expertise via a prior on the optimization. Specifically using PyMC3 though, I place a gamma prior on L and a half Cauchy prior on eta in our running example. This results in a posterior GP here. Now we see that by having this hierarchical structure for our GP, the fit improves from what we had before. As some of you might have already known, defining a hierarchical structure for your Bayesian model by placing priors on parameters that define other variables is something that PyMC3 in general does really well, and it's actually what attracts me the most to the library. Okay, so far we have talked about building Bayesian models on mathematical objects, either individual variables or functions, and performing inferences on them. These techniques are not unique to machine learning, and in fact, I'm pretty sure that the statisticians watching this are more familiar with them than I am. What is unique to machine learning, though, is the technique of placing priors on parameters of a machine learning model, and then use Bayes' theorem to obtain the posterior distributions of these parameters. These posteriors then induce a posterior predictive distribution on the target variable that we'd like to perform predictions on, which gives us the same benefit of having a belief on a target as well as uncertainty quantification. The classical example of this is Bayesian linear regression, which we will consider next. As a refresher, in a linear regression problem, we have a set of features or predictors x and a target variable y, and we assume that there's a linear relationship between them. We can encode this assumption using this equation where W here is a vector of random coefficients or weight variables, and epsilon is the residual or noise. Our goal is to find the value for W that will result in a good fit for a linear assumption. The exact definition of a good fit is up for interpretation, but the simplest way to solve this problem is to find W such that the sum of squares of the residuals is minimized. This method is actually called least squares, and if we were to do a bit of algebra, the optimal solution for W can actually be found analytically. With the optimized W, we have in the end a hyperplane that roughly goes through all the points considering all the points in our training data. In the 2D case where we have just one feature, this becomes the so-called best fit line that many of us are familiar with. So how would we solve the same linear regression problem in the Bayesian way? I mentioned that W is considered to be a vector of random variables, so the first thing that comes to mind is to place a prior on this object. The most common way to do this is to say W follows a multivariate normal distribution, so each of the coefficients in W has a normal prior. We also assume that epsilon is Gaussian noise with unknown standard deviation sigma. This sigma, which is a positive random variable, can also have its own prior. So with all of these priors set up, we can compute the likelihood of our observations y being using a linear assumption, and from there use Bayes' theorem to compute the posterior for each of our variables, W and sigma. Again, what we'll have in the end is the posterior belief for each of the variables, which together also induce a posterior predictive distribution for y. This helps us do point estimation if we'd like to extract out just a single variable for y. More importantly though, we can quantify the uncertainty we have about y. So for example, using this specific 2D toy example, we can plot out the credible interval for y, which somewhat looks like what we have with the GP, but here our belief about y is constrained to be linear with respect to x, so our credible interval looks a bit different. However, the benefits are still the same. For each point that we're predicting on, can naturally extract out a belief as a probability distribution about y. Here we can compute the mean or the mode for y, and that will give us an output that is almost equal to the least squares method in many cases, but we can also say how much uncertainty we have about this output. Again, I want to make a point about how what we have here is objectively better than the output from the least squares method, which again highlights the benefit of a Bayesian framework. Last note I want to include about this topic is the procedure also extends beyond linear regression and to polynomial regression on other models as well. As long as we have a predefined relationship between a features x and a target y, we can place a prior on x, on the parameters that we have, and establish a likelihood for our observations, and everything else can follow. An example of this is neural networks. Some of you might be already familiar with this machine learning model, but in a classic neural network, we have a graphical structure that consists of many layers of nodes. In each node, the linear relationship that we just talked about is applied to the input of the node, and the output y is then put through a nonlinear transformation. The final output of the network is what's used to perform predictions. The collection of these weights, called also W in all of these nodes, is the parameters of the neural net that are optimized during training. So if we were to apply the same Bayesian framework to this neural network model, we could simply again place a prior on all of these weights and perform Bayesian inference to obtain first the posteriors for the weights and then the posterior predicted for the final output. And this will give us the same exact benefit that we've been talking about, an updated belief about the output variable that defines not only the most likely value, but also the uncertainty in the value. The case of Bayesian neural nets is a bit more special though, since maintaining and updating a belief about the collection of network weights, which is typically extremely large, is infeasible using simple sampling strategies. So we would need to use variational inference, which is quite well implemented in PyMC-3. On this topic, Thomas Vierke actually has a great talk at PyData, which I'm linking here, so you could check it out for yourself. Okay, and that's the end of what I wanted to talk about regarding Bayesian modeling, specifically making Bayesian informed predictions. Now we will transition to Bayesian decision theory, where we consider the process of making Bayesian informed decisions. As we will see throughout this section, Bayesian decision theory consists of two main components: maintaining Bayesian beliefs about unknown quantities, which we just talked about, and using those beliefs to maximize the utility function. The term utility function denotes our evaluation for different outcomes of an unknown event. The function denoted as U basically maps a decision leading to an outcome, which is random, to a specific numerical value, so it gives us a way to compare and express preferences over different decisions and outcomes. The concept is unique to each problem and sometimes even unique to each statistician, but as long as we have a well-defined utility function, we will be able to say things about the Bayesian optimal decision, denoted as D star here, which is the decision that will, in expectation, lead to the best outcome, according to the current state of the world and our utility function. To become more familiar with the idea of using the utility function, we will go through a quick talk example, where we derive the best strategy for The Price is Right. A setup here is a modified version of The Price is Right. We are competing against another player in a game where we have to guess the price P of a product using just a single number, denoted as G here. Our opponent has already made her guess to be P bar. Now, if our guess is above the actual price, then we won't get anything, in which case our utility is 0, and the same goes for our opponent. If neither of the guesses are above the actual price, the person with the closest guess will win the product. If we win, our utility will be the actual price of the product P, otherwise it will be 0. So we do have a prior belief about P expressed as a normal probability distribution. Our task is to also make the Bayesian optimal guess, which is the guess that has the highest expected utility. Now, the technique to derive the optimal decision in a Bayesian framework is relatively the same across problems. We first consider the utility of each action given the actual price, and then marginalize out that price according to our belief. Specifically, our utility is 0 if our guess G is larger than P, regardless of what our opponent's guess is. In other words, U of G given P is 0 if G is greater than P. If G is smaller than P bar, smaller than P, then our utility is also 0. Otherwise, U of G given P is P if G is greater than P bar but smaller than P. Then for each value of G, we compute the expected utility as expectation of U of G as the integral of all the U of G given P marginalized over the different values of P's. This can be approximated again by trying samples of our predictive distribution about P and computing U with the rules that we have. Finally, we choose our guess G to maximize this expected utility. And that is the general process of deriving the Bayesian optimal decision. Using the same procedure, we can write a function that takes in values sampled from this predicted distribution to represent our belief and plot out the expected utility as the function of our guess. Let's say for a specific example, we have a predictive belief about P as a Gaussian with mean $100 and standard deviation 10, and our opponent has guessed at 75. Here I'm showing the plot that denotes the expected utility as a function of potential guesses. We see that everything below 75 has an expected utility of roughly 0, since our guess is lower than our opponent's and we're most likely not winning given our belief. To obtain the Bayesian optimal decision, we'll simply locate the maximum of the plot and get the corresponding guess. In this case, it's a number just above 75. This makes sense since we only need to make sure that our guess is above our opponent's guess, so there's no value in going too far away from 75 and risking going above the actual price P. This is why the expected utility quickly drops to roughly 0 after this point. Of course, here our opponent is at a total disadvantage because she has to guess first, so the actual format of the show is not this simplified version. But overall, I hope that via this example, we can understand the concept of the Bayesian optimal decision and how to derive it. Moving along, we'll start talking about actual problems in machine learning that can greatly benefit from a Bayesian perspective. We'll start with one of the most canonical problems in Bayesian decision theory literature, the multi-arm bandit problem. The setting we have is the following. We have k slot machines, 1 to k. Each returns a coin with probability theta I when its arm is pulled. We only have a limited number of pulls n available to us. Our goal is to sequentially pull the arms of these machines so that our expected number of coins, which is typically called the reward, will be maximized when we run out of the pulls. The difficulty of this problem lies in the randomness of the reward returned by each machine. Say at a given point, we have identified a machine that returns a good chunk of the coins when it's pulled, and it's the best return rate that we have seen so far. But there's also machines that we haven't pulled yet, or we have only pulled once or twice, so we don't even know what their actual return rates are roughly equal to. This is generally called the trade-off between exploration and exploitation that is inherent in many decision-making problems in machine learning. A solution to the multi-arm bandit problem is a way which we'll call a policy of deciding which arm we should pull so that our chances of identifying the true best machine as quickly as possible are maximized. There are some naive policies that we can immediately think of. For example, a greedy policy will always choose the arm of the machine with the highest observed return rate so far at the risk of not exploring enough and failing to identify the true best machine. A purely explorative policy, though, will choose a random arm every time, so its expected performance is simply the average return rate across all machines, which is not that great. The question is, can we come up with a principled way of choosing an arm to pull at each iteration to balance between exploration and exploitation? Overall, many real-world problems can actually be posed as multi-arm bandit, such as designing clinical trials where we like to investigate the effect of a drug while minimizing adverse effects on patients, or personalized recommendations where we want to suggest customized products to a customer. Now, one way we could immediately apply a Bayesian framework to this problem is to model the return rate of each machine and its outcome as well in the same manner as the classic binary event example. Specifically, we place a prior, for example, uniform on each of the theta I, so the outcome of each machine where the machine will return a coin if pulled follows a Bernoulli distribution with unknown parameter theta I. Now, at each iteration, we can obtain a posterior predictive distribution for this outcome with respect to every machine, and from there have a way to quantify our uncertainty about them. That still leaves open the question of how to design a policy to pick one arm to pull at each iteration. A good policy, again, should prioritize arm with high expected return rate and or high variance in the posterior predictive distribution of the outcome, corresponding to the trade-off between exploitation and exploration. One potential solution is to design the Bayesian optimal policy, which basically chooses the arm that in exploitation will result in maximum current plus future reward. For example, if we only have one pull left, the Bayesian optimal decision is to greedily pick the arm with the best return rate. However, if there are two or more pulls left, the value of pulling an arm depends on not only the immediate expected reward from that arm, but also the expected impact it will have on our future beliefs and decisions, conditioned on the outcome of that arm. Overall, computing the Bayesian optimal decision is intractable when the number of pulls remaining is greater than 2, so we need some other policies that approximate this optimal policy. Also to quantify how good a policy is, we typically use measure co-regret, which is the difference in utility between a given policy and always pulling the unknown optimal arm. It has been proven that the best we could do is a regret that behaves like a logarithmic function of the number of iterations t, so our goal is to have policies that have regret of this behavior. Here we'll discuss two of the most popular policies of this multi-arm bandit problem, UCB and Thompson sampling. There are many versions of UCB or upper confidence bound policy, but in one Bayesian variant, we assign a point to each arm using this formula, which is a credible interval upper bound of the posterior distribution of the return rate variable. At each iteration, the arm with the highest score will then be pulled. We see that this policy naturally balances between exploration and exploitation. By giving this upper credible bound, since if an arm has a high empirical return rate, then the whole posterior credible interval will take on higher values. On the other hand, if an arm has not been pulled many times, then it will have a fairly flat posterior belief, and the upper bound of the credible interval will also have a high value. Of course, if an arm is obviously not optimal, its posterior distribution will take on lower values and its UCB score will then be low. So we basically deprioritizing it from being chosen. By using this score rule, we will sequentially explore the set of available machines and converge on one that gives us the best reward. And that is the idea behind UCB. The second policy we'll take a look at is called Thompson sampling. Unlike UCB, where the procedure of choosing the next arm to pull is deterministic, Thompson sampling is a randomized policy, meaning that when faced with the same information, it's not guaranteed that the policy will make the same choice every time. Again, at each iteration, we maintain a posterior belief about h theta I as a probability distribution. Thompson sampling tells us then to sample from these posteriors, which will give us a rough estimate for h theta I denoted as theta I bar. Then we simply choose the arm corresponding to the largest estimate theta I bar, and that will be our decision for that iteration. As you can see, this procedure is randomized as the sampling step is inherently not deterministic. The intuition behind Thompson sampling is quite simple, but also very elegant. If we are very certain about a belief about a specific theta I being the maximum return rate, then its posterior distribution is very concentrated around a relatively large number, which means a sample from this distribution will be very likely to be close to that large number as well, thus giving making arm I more likely to be chosen. On the other hand, if we are very uncertain about theta I, its posterior distribution is more widespread, and it's also likely that a sample from this distribution is a large value, again causing arm I to be chosen. This sampling and choosing the largest procedure naturally favors posteriors that are either concentrated around a large value, in other words, exploitation, or have more uncertainty and are more widespread, or exploration. Sid Ravinutala recently published a great blog post on Thompson sampling in the context of COVID testing, which I'm linking here and highly recommend you check it out. Okay, so that's the problem of multi-arm bandit and the two most common solutions to it. Theoretically, we can actually prove that the expected regret resulting from applying either of these solutions does have a logarithmic trend, so it's a good guarantee to have when these policies are applied in real-life situations. Now I want to move on to a somewhat related topic called Bayesian optimization. In general, the term Bayesian optimization does not denote a specific algorithm, but a Bayesian framework of decision-making for optimization problems. The setup for such a problem is simple. We have access to output of a function via queries, but not its gradients or its functional form. And sometimes the function we want to optimize doesn't even have a functional form. So all the gradient-based optimization algorithms are not applicable. Also, querying this function is expensive, either costing a lot of money or time-consuming or other definitions of cost. So the number of queries we can make to the function is very limited. Our observations might also be noisy or not exactly the function values. The go-to example to motivate this problem is hyperparameter tuning of neural network models. As you probably know, most of the time we want to set these hyperparameters so that the predictive performance of the model increases. This could be accuracy, area under the curve, or some other metrics, but it's almost impossible to tell the functional form of these metrics in terms of the hyperparameters, or if one even exists. Also, rerunning the whole neural net with a new set of hyperparameters can be quite time-consuming, since neural nets can take a long time to train. The question laid out before us is that how can we design an optimization policy of sequentially making queries to the objective function so that the maximizer of the function is identified when our queries run out? Recall that in the multi-arm bandit problem, we model our belief about the return rate theta I of each machine using Bayesian framework. The same can be done in this problem as well, but here we don't have individual latent variables theta I that we need to worry about, but we have an entire function that we'd like to model and update a belief with new observations. As you can already guess, this is where Gaussian processes come in. A GP prior can be placed on a function to help us model a belief about the value of the function at each of the points in the domain. Also, this gets updated with new observations to reflect a posterior belief about the function at unobserved points. Our task is again use this posterior belief about the function modeled as a GP to make informed decisions as to where to query the function, so that when our budget is depleted, we can identify the maximizer of the function. So far, you might have noticed that there's a parallel between Bayesian optimization and multi-arm bandit. In both problems, we are faced with a decision of choosing where to evaluate next, either an objective function or among a set of slot machine arms to pull. In multi-arm bandit, we model individual return rates using the Bayesian framework that we talked about. Well, in Bayesian optimization, we use a GP as the equivalent for the function. In multi-arm bandit, we have the Bayesian optimal decision to be intractable except when we only have 1 or 2 iterations left. Same thing goes for Bayesian optimization. It's quite easy to see that the optimal decision is intractable except for the very last decision. If we have more than 1 query left, we would need to iterate through all the possible queries, which are infinitely many, but also condition each possible outcome of each query to look ahead. Therefore, in Bayesian optimization, we also need to design policies that approximate the Bayesian optimal one. At each iteration, we have the posterior predictive distribution of the function value of each point in the domain. This object gives rise to some of the most common Bayesian optimization policies. For example, the probability of improvement policy calculates the probability that the function value of each point is greater than the current maximum function value that we have observed, denoted as y bar here. This requires us to compute the CDF or normal distribution among points in the domain, which is quite easy to do. The expected improvement policy, on the other hand, calculates its scores as the expected improvement from the current maximum function value y bar and chooses the point with the largest score. The posterior predictive distribution also allows us to use the GP equivalent of the upper confidence bound policy, which again computes the credible interval upper bound of each unobserved point in the domain and chooses the maximizer. We see that similar to what we have seen, all of these policies again balance the trade-off between exploration and exploitation by prioritizing points with large expected value or large uncertainty in its posterior distribution. Given the posterior predictive distribution of the objective function, we can also consider a mathematical object that is the location of the true maximizer of the function x star denoted here. Specifically, we can consider the distribution of this object. This object motivates several other optimization policies that seek to minimize the uncertainty about x star via their queries such as entropy search or predictive entropy search. If this idea sounds strange to you, a minimal equivalent case is binary search of a sorted array. By querying the number in the middle of the current subarray in each iteration, we effectively minimize our uncertainty about where the number we're looking for is. Entropy search and predictive entropy search work roughly in the same manner, but the target of the search is the location of the function maximizer. Interestingly, Thompson sampling also has its own analog in Bayesian optimization, where we first assign each unobserved point a score equal to the probability that the true function maximizer is at that point. Then we randomly sample the points with probabilities proportional to these scores and query at the point that has the largest score. Again, these policies are motivated by finding the location of x star, powered by our GP belief that we maintain on the objective function, which is quite a unique technique that's only possible within the Bayesian optimization framework. Implementation-wise, Python offers a wide range of good libraries that implement Bayesian optimization policies. Here I want to highlight a relatively new library called PyGPGO, which integrates a PyMC backend with GP modeling. Dan Foreman-Mackey is one of the authors of this tool, so I'm highly recommending checking it out. And with that, we reached the end of what I wanted to cover regarding Bayesian optimization. Now I want to briefly go through some other more exotic problems in machine learning where Bayesian decision theory thrives. First, we have the subfield called active learning, where the goal is to identify minimum training data that will give a given ML model the best predictive performance. If you're familiar with support vector machine classifiers, you might remember that if the training data is reduced to just the support vectors, which are the data points that are on the classification boundary, then the resulting trained model will not change. The idea is generalized in active learning, where we want to identify the smallest set of training points to train our models without sacrificing any predictive performance. Typically, this is used when obtaining the label of a data point is costly in the same way as Bayesian optimization. It's either expensive, time-consuming, or undesirable to do many times in some other way. Related is the active search problem, where we still have the constraint on the number of queries we can make, but the goal is to identify as many members of a rare class as possible. In other words, this is an active learning problem where we like to maximize recall. The ability to actively search for and make queries that are optimal and expectation with respect to a specific goal comes straight from our belief about our environment represented as probability distributions and worked out using Bayesian decision theory. Results from these subfields can lead to cheaper and more efficient ML model in applications where, again, labeling is costly and uncertainty plays an important role, such as clinical trials, fraud detection, or scientific experiments. This concludes my talk on Bayesian methods in machine learning. Overall, we have discussed two specific topics, Bayesian modeling and Bayesian decision theory in the context of machine learning. I hope I have convinced you that going from Bayes' theorem, we can design Bayesian frameworks to address problems in ML in a more informed, principled way. The second point that I wanted to make is PyMC's ability to allow fast, easy building of probabilistic models, especially ones with hierarchical structures. Thanks again for tuning in, and if you have any questions about the materials, please head over to Discourse and participate in the conversation there.